Okay, so before we go to the break, I will try to introduce you some of the concepts of data-centric confidentiality. So the basic idea for this data-centric confidentiality is that all content is encrypted. Like whenever you produce the content, you encrypt it. And the problems here we have is how to define a policy and how to execute this encryption policy so the only authorized people get decrypted, and there's only there's a limited overhead in distributing the keys. So what we have in mind is a so-called name-based access control, and I will go into detail and show examples of the actual names of the encryption keys or decryption keys. But effectively, what we have in name-based access control is entity that defines the policy. So in this terminology of an access control is a access controller. In our example, it would be base defining who is allowed to access PLI data. Producers, effectively everybody in our notional environment, and consumers also could be all elements in our notional environment. Again, so for the purpose of to minimize overhead, so we designed the system to have a combination of public key cryptography and the symmetric cryptography. So specifically, what happens? There are several types of public and private key pairs. So one important pair is a key encryption key and key decryption key. So this pair effectively defines the policy for the whole data set. So within this data set, effectively, whoever can get access to the decryption key, effectively what the access manager needs to do is to encrypt decryption key using the private key of the the guy who is authorized to get access. And there's another another part that I just mentioned is the symmetric key part. So the actual data that is being generated is encrypted actually using symmetric key. And that symmetric key is for encrypts the data, and the symmetric key itself is being encrypted using key encryption key. And I'll try to get a few more details in this illustration. So we got to the point of having the actual data produced, data being encrypted using symmetric key. Symmetric key is encrypted itself, and we're transferring the data to some transferring data in the network. So data is always protected, no matter where it's cached, is stored, or in whatever path is being taken. It's secure. So you just need to get the proper keys in order to get access to it. And what's going to happen? You also can retrieve the symmetric because it's also a data packet, and the data, actual data identifies the symmetric key by name, so you can fetch it. And further, you can also receive the decryption key because that one is also identified as part of the content key, and I'll give you an example in a few seconds. And we can if you can retrieve the decryption key that has been created for you, then you can get access and effectively can decrypt the decryption key, and you're supposed to decrypt the content key and finally decrypt the content. So it's a little bit obscure description, and I'll try to give you a few more, even more obscure potentially, but it's more interesting examples of how NDN names, how this power of hierarchically structured or just structured names can be utilized for the purpose of defining the policy for the data, as well as to retrieve the policy and enforce the policy and control access to the data itself. So in this specific example, we're still using basically the same naming conventions that Tamer has introduced. So we have apps, PLI, global, something else, but also introduce an additional component called NAC in here, and a key for the purpose of a key encryption key and some other information. The reason I'm kind of emphasizing this part here, so as Alicia mentioned, names are used as part of the transport protocol to do kind of dispatching of all the requests and kind of how to actually serve the data. So in this specific case, this NAC component identifies that if this interest reaches the host, it needs to be dispatched to this access control application. That access control application can retrieve, can give you actual data that you've been requested and kind of effectively identified by the rest of the prefix. So that's one part of playing games with names. The other part, which is even cooler than that, is kind of a naming of the key decryption key. In this format, what you can see on a slide, key decryption key named, at least the prefix of the key decryption key, is almost identical to key encryption key, with exception there's a key replaced with key. But then there's a kind of interesting part that you can actually specify by which key, by the kind of name of which key, this key decryption key is being encrypted. So effectively, in this specific case, the access manager needs to create a bunch of policy, encrypted version of key decryption key, encrypted by different participants in the system. So in this case, it's by carrier, by Humvee, or by specific Humvee, and some other ones. And this part is known to everybody, not known to everybody, but known to a person who has the key, so you know your name. And the part of the access control is identified as part of the kind of the actual data packet has been retrieved. So you can always construct the name, and if you've been authorized for access to this naming policy, you will retrieve this encryption key, you will be able to decrypt it and proceed with the decryption process. So a few more things that I can identify here. So this is actual data production, where the data being encrypted by following this specific policy. And kind of effectively to follow the policy, you need to fetch key encryption key. And effectively just send in the interest for the key encryption key. And this is the public key you'll be using to encrypt the data. And kind of the naming convention for that one pretty much follows what I just described. And just additional illustration of the actual data packet that being created in this case is a name that Tamer showed before. With a small addition, there's also a name that identifies the encryption key. So there's an app PLI global carrier CK1. So this is the encryption key that is used to encrypt the data. And as soon as you at the moment you send interest for this in CK, just by this prefix, you will also discover what is the name of the policy that's been encrypted. Unlike kind of the conversation that Tamer mentioned about this must be fresh, not must be fresh, so this doesn't really apply in this case. So you just request data by this name, and there's only one kind of encrypted version of the CK, and it doesn't really matter whether it's a stale or not stale, fresh or not fresh. So you just send this message. And the final part for the consumption, again, it's just illustration of additional names of how things have been retrieved. You retrieve the data packet identify things, what you need to do. From that name for the CK, you retrieve the CK, from the CK identify the policy, you retrieve the actual key if you haven't retrieved it before, and you got the access or didn't get the access. Okay, for the sake of the time conservation, I will talk about the signing certificates in more detail as part of the different application scenario. And for this part, I will try to conclude with a small statement that the process of kind of what I just described is powerful in the sense that it does not require an online presence of all parties in the system at the same time. So, for example, the access manager, or the base in this specific case, can have granted the access kind of long time ago. And as long as this access or encryption key of encrypted version of a key decryption key exists in the system in some caches, then you have the access. And the same thing applies for the data itself. Like, the data is still floating, it's in encrypted form. As long as it still exists and you can fetch it, you will have access to the data. Of course, it raises a few concerns about kind of revoking the access to the data, but that's quite a different conversation.